to have them here. Abir and Rishabh.
Okay. Can you hear me? Okay. Okay. So, yeah, sorry. So thank you so much for joining us for this tutorial. Thank you so much for the invitation, the organizers of the conference. I think so far all of us have had have enjoyed the conference. It's been really a set of awesome presentations and lots to learn from. So today, now in the next 2 hours, myself and Abir, we are going to cover a few topics within the framework of optimization, specifically combinatorial optimization. And we're going to look at, some theory and some applications of this in machine learning. Okay. So I'll give a, kind of an outline of the tutorial, okay, and how it's going to be structured. So initially, I'm going to give some motivation of this tutorial, and a lot of this is going to be, related to problems around, efficient learning, robust learning. I'm going to talk about some theoretical, advances in this area. So we're going to talk about some models for data summarization, some combinatorial, functions and models. Talk a little bit about combinatorial optimization, and then Abir will talk a little bit about, some neural, some work in neural submodular functions. And then in part 2, we're going to focus on applications, and specifically we're going to look at 2 families of applications. One around active learning in the real world, and the second in human-assisted learning. So I would like to say that, there are a lot of different applications, but in the interest of time and, in the interest of focusing, we're going to just cover, 2 specific applications in a little bit more detail. All right. So, kind of a high level, right? Okay. So kind of a high level that you guys can hear me at the back, okay? Okay, thank you. So there's a lot of impact of, deep learning and machine learning, right? So, ranging from several applications, from personalization, robotics, autonomous vehicles, we have kind of deep learning and machine learning having an impact today. And as a result, there's been, in some sense, deep learning models require a lot of data, right? So there's been an explosion of the amount of data required, right? And naturally, this data also is used to train machine learning models, right? So large amounts of data are being generated by, humans and machines. And in some sense, a lot of the problems kind of boil down to how do you find things of interest? How do you find something that, you can kind of find in the needle in a haystack, right? So how do you find the needle in a haystack so you can improve the performance of the model? Instead of just feeding it, billions of either text, sentences, documents, or maybe images, we can maybe find, systematically find things that are of more interest, and that way make things more efficient. Okay. So you have data hungry, kind of the data hunger of these deep models. And, this is kind of obvious, right? With all the deep models that have been, coming up, you have growing number of examples here that are used to train these models. And obviously, as you throw in more data, you are getting better improved performance. So there are several problems. In this tutorial, we're going to talk about only a few specific applications, but the theory that we'll be covering can actually address a lot more of these problems, right? So the first problem is the training costs of deep learning, right? So you have, these staggering costs and a staggering amount of time, right? So for example, training a BERT model today can cost ranging from, $10,000 to $200,000, right? And this is oftentimes because you need to run multiple runs of, BERT to kind of figure out, the right configuration of hyperparameters that is, useful for your task. The second is training, a single deep model with neural architecture search, right? So the moment you do AutoML or neural architecture search, again, this blows up the amount of compute. I mean, the cost. The third is, the amount of time required, right? Which also is very large. And, these are some examples of, vision tasks where you kind of require several GPU days. And again, this is something which may not be a problem for, big companies today, but obviously for smaller academic groups, for smaller startups, this is a major problem, right? So one of the main kind of important things of democratizing deep learning or democratizing machine learning is really making, machine learning and deep learning available so that it can be trained much more efficiently, right? The second kind of, again, the kind of second issue with large amounts of data is that labeling these large data sets is expensive, right? So labeling a 50,000 image data set will cost, for example, $5,000 to $30,000, right? Same for, for object detection, 3D object detection, for like autonomous driving applications, and for text classification, right? So kind of a staggering cost here of training, of kind of labeling data sets today for us to use. And finally, real world data sets have, a lot of noise and imbalance issues, so there is like an imbalance in classes, imbalance in slices. There is a lot of, label noise that is there, So one of the challenges is you can't just arbitrarily kind of get smaller data randomly, right? So big data is very different from small data. So this is kind of seen a number of times, but very early, in fact, this was observed that just with a small amount of data, they initially found, results to be very discouraging on this kind of image completion task. But the moment they added more amount of data, they saw that, the performance increased, right? So big data definitely is needed, right? But at the same time, there are several problems, right? So you have, big data is plagued with redundancy. And in some sense, we want to be, kind of select the right small, right kind of small data. Okay. So this is how small data looks like, right? So if you just kind of create a random subset of small data, you are not really representative of the entire set, right? So you might have some biases. As you get more and more, the bigger amount of data, you get a better representation of the entire space. But then a core data set or a core set or a summary is having the most, representative instances of this data set, right? So I'd like to say that there are several tutorials actually online available, in various conferences, a few of them given by us as well, on this topic. So, this is not a first tutorial, but, a lot of what I'll be covering is kind of inspired from a lot of these earlier tutorials. Okay, so having motivated this problem, right, and again, we're going to be talking about concretely two specific applications, in the next, in like the later part of this tutorial. So we're going to start a little bit by understanding how we can develop some of the theory to address this, right? And of course, this is one approach. There are many approaches. If I were to, maybe spend an entire day, still I would not be able to do justice to, the amount of content that is there today, now the amount of work that is done in this space, right? So I'm going to cover some representative ideas in this space. Okay. So I'm going to talk about this from a viewpoint of combinatorial optimization, right? And specifically, we're going to look at, combinatorial subset selection problems, right? So you have a ground set here, V of, instances. This is your data set, right? And the space of functions F is 2 raised to V, right? So it's a ground set. So it's an exponential set of all possible subsets of this ground set, right? So a set function is where you take a subset and then you have a value of the subset, right? So why is this important? Imagine you have a subset of your data set, right, that you're selecting to maybe give a human for labeling, or you have a subset of the data set that you're selecting to, train your model for compute efficiency purposes, right? So whatever be the downstream application, the question is, how do you design this subset and what are things that you want, right? So you want things, for example, that you want your subset to be representative of the entire set, right? Or you want your subset to be a diverse subset, right? Which doesn't have redundancy, so on and so forth, right? So general set function optimization is very hard, right? Because you want to search over all possible subsets. So this is a hard problem, right? So what if there's some special structure? So one specific structure is, the class of submodular functions. And I'll kind of give, a few examples of these submodular functions, but we'll start with a very simple kind of intuitive example, right? So imagine you have a set of balls and, an urn, right? So essentially over here, define this function f as the number of distinct colors of the balls in the urn, right? So over here, there are two distinct colors, right? The moment you add a new color, a new ball, the number of distinct colors increases from 2 to 3, right? Whereas in this case, which is a superset, you already have, blue ball. So adding a blue ball, basically the gain in, adding this new ball, the gain in the number of distinct colors is actually 0, right? So there's a diminishing returns, right? So you have a smaller subset, there is more information. Think of this from an information content perspective, right? When you have a smaller subset, a new item can add more information as opposed to a larger subset, right? So that's basically the intuition of broadly of these combinatorial functions, and specifically submodular functions, right? So you have this diminishing returns property, right? And if you have additive costs, right? So these are called modular functions. So if your function f of s is just the sum of the weighted, weights of each of the element in the set. So if you have 3 items over here, each of them has a cost. If the cumulative cost of all 3 is just the sum of them, right? Then basically this function is just called additive or modular, right? So a set function is called monotone if as you have, as you increase the subset size, the value of the function grows, right? So basically where A is a subset of B, f of A is less than f of B. So several functions, including information gain, entropy function, influence in social networks, many of these functions are natural, right? So why are these class of functions very natural from a summarization perspective? So imagine you have an image collection like this, right? And now you have a subset and you have a superset, right? So think of this as the information content of, this subset and a superset, right? So now I have 2 images, I have some information, right? So this is a scene over here where there's a sofa, there's a boat over here, there's a sofa, there's a boat, but there's, another scene over here, there's a car and there's a person, right? So you have information content. This obviously has more information compared to this, right? But this is not submodularity. This is just monotonicity, right? So as you have larger subsets, this has more information compared to this. Now, submodularity says that as I add one more image, right, this image is more redundant in the larger subset as opposed to the smaller subset, right? So since there are no people over here, the new image adds more information to this smaller subset as opposed to this larger subset. Okay, so this is the intuition of submodularity, and a lot of functions that you can design actually, turn out to be submodular. Okay, so the basic, kind of TLDR over here is information gain reduces with larger sets. So as the context of the set grows, the gain in information of adding a new item shrinks. Okay, so this is very natural from data selection or like any machine learning application, right? As you increase the amount of training data, you have a diminishing returns in performance, right? As you go from maybe 1,000 images to 10,000 images, you have a large jump in accuracy. As you go from 10,000 to 100,000, you might have, a more kind of medium kind of increase in accuracy. But as you go from 100,000 to maybe 500,000, your accuracy starts, kind of plateauing, right, after a point. So this is exactly, this diminishing. Of course, this depends a lot on the kind of model and so on and so forth, but generally this is what you see in machine learning. So a lot of these natural problems, you have this kind of diminishing returns property when you look at learning curves, and a lot of these can be seen from this perspective. Okay, so what are different kinds of combinatorial functions, right? So you have representation functions, okay? So representation functions, one example of representation functions are, for example, the facility location function, right? So facility location function basically says that you have a set of facilities over here, right? And so you have a set of, items you want to cover, like these are basically people, right? And you want to select facilities so that you can cover all of these people, essentially, right? So what this function is saying is that I have this ground set V over here, and for every instance here in my ground set, I want one representative. So this is very similar to what you would expect from a clustering, right? Because when you are clustering, you have your medioids or your representation or your means, right? So this is in fact very similar to k-medioid clustering, right? Because when you have k-medioid clustering, you want one representative amongst your set of data points, which are your exemplars, and then these form your representatives, right? So this subset X, when you maximize this specific location, you exactly get, the medioids, okay? There are a few other kinds of submodular functions, but all of these are naturally representation, right? So you want, given your entire data set, you want to find representative set of items. And typically what representation means is that you would find, you would try to cover every possible cluster in your data set. Okay, so think of a representation task like this, where you have different kinds of images, right? And you're selecting a subset of images over here, right? Maybe a representation function will ignore outlier because you just have one outlier image like this, which is probably not as useful. It's just a hand covering a camera, right? But these are more representative images, and from each cluster, it will pick one. Okay. So representation functions pick centroids, right? Okay, so there is, another variant of this function called the k-center function, where instead of the sum, you have the min. That's also a representation function, right? So this is also called the metric k-center problem. Okay, so another kind of way you can model kind of submodular function, that, kind of another facet that submodular functions model is the facet of diversity, right? So what is diversity? So diversity basically says that given a set of points, I want to pick points that are as far away as possible. I don't care about covering the entire set. I just want to have points that are as far away. So naturally, imagine you have, a scenario like this. A diversity function will actually pick outlier, right? Because outlier is very far away from all the other, all the other points, right? So, the kind of from a modeling perspective, a lot of these functions have very different modeling characteristics. So the goal of diversity function is to pick items that are as different as possible from each other. Okay. Finally, you have coverage functions, right? So coverage functions are functions where you basically want to cover a set of items, right? So you have basically here concepts, right? Say, for example, cat, dog, bird. These could be words in a dictionary, right? And my data points or my instances are essentially, say, sentences, right? Or they could be documents. So I want to find a subset of documents that cover as many important sentences or important words as possible, right? So this is a coverage problem. And the same can be from a set of images, right? So you have an image that covers a car. If one image covers a car, then there's no point of adding another image that covers a car, right? So again, this is from a coverage perspective. You are trying to find a subset of instances that cover as many concepts as possible. Please stop me, by the way, if you have any questions at any time, okay? So I'm just kind of going through the modeling characteristics of a lot of these functions. Okay, so a slight variant of this is where you assign a probability. So instead of saying, 0-1 coverage, where you either cover an item or not, you can assign a probability, right? You can say that this image covers a car with a probability 0.8, right? It maybe covers, a green, suppose there was something like a greenery scene or trees behind, it might cover, another probability, right? So you could have more than one, concepts that are covered with different probabilities, and this function accounts for taking the probabilities in your coverage. Okay. In the interest of time, I'll actually go through this very fast, but you can also have feature-based functions where you have features, like deep models today, you have features, and then you want to select a subset that covers as many features as possible. And you have, these deep submodular functions where, you have kind of several layers of these feature-based functions. So in fact, Abir is going to talk more about deep submodular functions, in the second part here. Okay, so now we are going to kind of move on to, kind of an important transition here and contrast, a lot of these combinatorial problems with information functions and information theory. Okay, so from an information theoretic perspective, imagine you have a set of instances here, like a set of sensors, right? And now say you have random variables x1 to xn, right, which are discrete random variables, and define x of s as a subset, of random variables indexed by this subset s, right? So xs is the set of random variables indexed by subset s, right? So essentially, the entropy of an individual random variable is defined like this, right? And you can now define the entropy of the entire set of random variables, right? So it turns out that given a set of random variables, the entropy of this set of random variables actually is a submodular function. So discrete entropy over a set of random variables is submodular. Not just that, you can actually then define information, mutual information, information gain. All of these kind of have natural properties related to submodularity. Okay. So we're going to kind of recall a little bit about information functions, right? So you have information theoretic concepts, like for example, entropy, right? You can define a mutual information. So given two sets of random variables, you can define the joint mutual information between two sets of random variables, right? Or you can define the conditional entropy as the extra information. So conditioned upon xb, h of xa conditioned upon xb is the extra information in xa conditioned upon xb. Okay, so which is defined in this way. The mutual information over here is the joint information between xa and xb, right? So given two sets of random variables is the joint information between a and b. And finally, conditional mutual information is the joint information between a comma b conditioned upon xc. Okay, so why are all of these important? So the reason why all of these are important is because we are actually going to finally connect them to several applications in machine learning, where we are going to actually kind of optimizing these functions, right? So optimizing over entropy, mutual information, conditional mutual information, so that we can do a number of things related to targeting, conditioning, and so on and so forth. Okay, so in the interest of time, let me just skip through all of this because a little bit more theoretical. What I'll do is I will define now a set of functions at a very high level, right, which are extensions of these submodular functions to these information functions, right? So you can think of the submodular function as an information function like entropy, right? And then the conditional gain that you saw with the entropic version, you can define a submodular conditional gain, which is the gain in information of adding a set A to set B, right? So if I maximize the conditional gain, I'm trying to find a set A that is as different from a set B. Okay. And the mutual information is the reverse, right? So this finds the joint information between sets A and B. So if I maximize the mutual information, I'm trying to select a set A that is very similar to a set B. Okay. So there are a few examples here, where okay, so maybe I'll talk about one example and see the intuition of this. Okay. So given the set cover function, which we saw, you are given a set of documents, and the set cover function basically is covering a set of concepts related to a document, right? So what is the conditional gain? The conditional gain is the weighted sum of gamma A minus gamma B. So is the extra set of concepts that is covered by A that is not covered by B, right? So if I'm trying to maximize this function, I'm trying to find a set that covers as many new concepts, given already what is covered by B. Okay. So in a similar light, the mutual information is actually a weighted sum of the intersection of the set of concepts covered by A and B. Okay. So if I were to optimize this function, I'm trying to select a set A that is very similar to a set B. Whereas if I maximize this function, I'm trying to select a set A that is dissimilar to a set B. Okay. So let me skip this and actually look at look at what this does in real life, right? So we are given here a set of items. Okay. So what is all of this? This is just a synthetic plot of a set of points, right? So I have a grid, a cluster of points over here, another cluster of points here. So there are 4 clusters and there are some outlier points. Okay. Now, if I maximize a submodular function, what happens? I select the points in blue, right? So I'm selecting points that are as spread out as possible, right? So this is basically, say, a representative or a diverse subset, right? Now, what happens when I have a query point? So I have a query point, which is this green point, right? And the moment I maximize the mutual information, right, I'm selecting points now which are very similar to this green query point, right? What happens with the conditional gain, right? So here I have this red point, which is my point P. So in this case, by the way, I just have one query, which is green, right? I could have multiple queries, okay? Now, if I have this red point, which is given as P over here, when I'm maximizing this function, I'm selecting a set of points that are as dissimilar to this set P as possible. Okay, so this is kind of the intuition, right? So these submodular functions kind of model diversity. With the submodular mutual information functions, I'm modeling similarity and diversity, right? Note one thing, that I have a green query point over here, but I'm not selecting all the points in this cluster. Why? Because I want diversity as well, right? So the moment I select one point, I don't want to select too many points related to this point, right? Similarly, over here, even though I don't select this cluster, I'm still diverse, right? So I am selecting a diverse set of points that is different from this point P. Okay. All right. So very quickly, I'm going to talk about some motivating applications of this, and we're going to actually talk a lot of this in active learning and human-centric learning in the next in the applications part. Okay. So where is something like this useful? Okay. So this is a mutual information function, right? So this is useful in active learning, where I have some rare classes, right? So I know that certain classes or certain slices are rare in my data set, right? So for example, imagine you have an autonomous driving scenario, right? Which in fact I have over here, right? So you have an autonomous driving scenario, and most of the data points here in your labeled set are all images at daytime, right? So you don't have images at nighttime, and particularly you don't have too many examples of motorcycles at night, right? So if you don't have too many examples of motorcycles at night, your model may actually underperform and not perform as well in detecting motorcycles at night. So essentially, what we want to do through this targeting, if we know that a certain slice or a certain class is rare, we can actually optimize this function and select more examples in active learning that is relevant to this class. Okay. Another set of examples here is, if you have a large imbalanced data set, right, in medical imaging, or if you want to do personalized, machine learning, like say speech recognition, right? And you have several accents, and now you want to personalize to a particular accent. Then how do you select instances that are similar to a particular accent, right? So all of these are applications where you want to kind of do this, this kind of mutual information function. And we'll basically, we kind of call this targeted learning, right? So a lot of applications of targeted learning emerge naturally from these combinatorial functions. Okay, are there any questions at this point? Yeah.
So yeah, so in your computation of mutual information, was that between two sets of examples or one query and many examples?
It's between two sets of examples. So you have a set A and a set Q.
So in the previous example, like the toy example you were showing.
Yes. So in the previous case, we assumed Q was just a singleton, right? But Q could be a set. So right now, Q is just a singleton of one data point. But Q could be a set of points as well. So then you will have similarity with multiple data instances.
But in general, we define mutual information for distributions or like larger sets. So how does the definition extend to a single query point and
yeah, so that's a good question. So mutual information from a information theoretic perspective, right? Information theory is defined on random variables. So what we have done is you can define mutual information between two sets of random variables. Okay. And now we have actually extended this to consider combinatorial functions. So all we do is just we replace the entropy function with any combinatorial function. In fact, in the interest of time, I'm not going through this, but there is actually a connection between the class of entropic functions and the class of combinatorial function. Like for example, a set cover function is a specific instantiation of, entropic function, right? So you have this nice connection, right? So in some sense, this can be seen as a generalization of these entropic functions without having to actually compute a probability distribution and actually, estimate entropy or mutual information. The problem with entropy and mutual information is very hard to estimate these quantities, right? Because you need to consider a joint distribution over a set of data points. So this allows for actually doing it in a combinatorial way and doing it much more efficiently. So think of it as a proxy. So it's a combinatorial proxy for, these information theoretic functions.
Thanks.
Any other questions? Yeah.
Only captures submodularity, or it is at the same time both submodular and diverse?
actually, because
That's a great question. So over here, this function captures two things, right? So it captures a query relevance, right? So when you maximize this, you're trying to find a subset A that is as close to Q as possible, right? Depending on how the closeness is measured by the submodular function. And it also captures diversity, right? So or representation, right? So the underlying function F is a facilitation function, it will capture representation and similarity. If a function is a log determinant function, it will capture diversity and similarity, right? So it captures both of these. So that's kind of, why these functions are, so useful in many tasks. Yeah, thank you. Any other questions? Okay, so again, this was at a very, very high level, but I want to make sure that the intuition, comes out. So I'll just repeat again, right? So the intuition is that, so submodular functions, have been well studied and well known for some time, right? These functions kind of naturally model diversity representation. They can be used for several tasks. Additionally, we have been defining these two kinds of functions, which are very similar to this. You can kind of model a query similarity if you have, a set Q, which you want to be similar to, or you can model dissimilarity here. So if you have a set P that you want to be dissimilar to, when you maximize this, you can kind of capture this, okay? But both of these functions still capture the properties of the underlying function, which is, diversity and representation. Okay. All right. So with this, I will talk a little bit about optimization, right? Because finally, when you define these functions, we want to think about how you can optimize them. Fortunately, these functions, sorry. So fortunately, these functions can be optimized very easily, right? So the master optimization problem looks something like this, where you maximize a combinatorial function, which is f of a. By the way, this function could be one of these as well, right? So it could be one of these. So it could be f of a, it could be the mutual information, it could be the conditional gain, any of these, okay? So given this master function, right, how do you optimize this, right? So this is kind of a broad framework of problems. There are several variants of this. I won't get into too much of details, because it's fairly theoretical, right? So I'll keep it at a high level for, this tutorial. But the master problem is where you have a set function like this, right? And you want to optimize this set function. Okay. So we will study a few variants, right? So the first simplest one is just monotone submodular maximization with a size constraint, right? So you maximize f of s such that size of s is less than k. So it's just a simple size constraint. The algorithm is very, very simple. So I think one of the most powerful aspects of why, this is so powerful and can be, implemented and used so much is because you can implement a greedy algorithm very easily, right? So just to kind of solve this problem, you can do a simple greedy algorithm. You start with the empty set, and then you iterate through the size k over here, and you add at every instance the element that increases the value of the submodular function the most, right? Just one step. So given a set I, you try to find in instance E, which maximizes f of Si union E, right? That's it. So it's a very myopic and greedy algorithm. I'm just looking at one step and I'm trying to optimize this. Okay. So over here, the constraint is size of S. Okay. So it turns out that in practice, this algorithm works very, very well, right? So on, for example, a sensor placement task, it was found that as you increase the number of sensors placed, that is K, that the two, the function values are very, very close, right? So the optimal value and what you get from the greedy algorithm. But there's a theoretical bound that shows that this value is at least 1 minus 1 over E times the optimal. And this value is nothing but 0.63. Okay. So it's theoretically guaranteed to be at least 0.63 times the optimal, right? But in practice, this factor is much larger, like almost 0.9 or 0.95 even sometimes. Okay. All right. So another kind of interesting variant is where every element has a cost. Okay. So earlier we just saw cardinality constraint, right? So I have a diversity function or representation function, right? And I have a large data set, like say ImageNet, right? And if I want to create a subset of ImageNet, which is 10% of ImageNet, right? So what is, if I have a representation function, how do I summarize ImageNet by creating a 10% subset, right? So I can train on this. So that could be solved from the earlier problem, right? Now, if I have a cost constraint, say my images are of different sizes, right? And each image has a size, right? So if you have different resolutions of images, each image could be of a different size. Then you could have a budget constraint, right? Where essentially the cost here is nothing but the size of each image, right? And finally, you have some megabyte size constraint that you want to do, right? Or say you have, a news article, right? And you want to summarize a news article, but you have a word limit, right? You can only summarize it with 250 words. So you can actually run a modified greedy algorithm, right? Where you essentially, okay, so first you run the standard greedy algorithm without taking the cost, and you run a modified greedy algorithm where you divide the cost of each item by the gain, right? So this is the gain of adding the element E to the set Si, and you divide by the cost, right? And then you pick the better of the two. So this actually has a good approximation guarantee, which is half times 1 minus 1 over E. Okay, so broadly speaking, the basic idea is variants of the greedy algorithm work very well for different kinds of submodule optimization problems. Okay, now there are a number of implementation tricks, right? I'll talk about it very, very quickly. One is that you can do a lazy greedy algorithm where you use priority queues, right? And that way, essentially what happens is that you don't need this order n square, but actually you can convert this to roughly an order n log n, okay? So if you have a naive greedy algorithm that looks like this, a lazy greedy algorithm is very fast. So the whole reason why, this framework is so powerful is that you can actually, summarize very, very large data sets, even, millions of instances, billions of instances, very, very efficiently, right? So towards making this more efficient, there is also a stochastic greedy algorithm where you make this even faster, right? So in the greedy algorithm, we were actually doing, this order n search to find the best element that needs to be added. You have to look through every single data point, right? So what you can do is you can randomly pick n over k times log 1 over epsilon, right? And just search amongst that. That's it, right? And run this for k times. So this algorithm, because you run this k times, the complexity of this is order n times log 1 over epsilon. So it's linear. Okay, so it's linear times multiplied by the function evaluation cost, right? And this is very, very fast. So if the lazy greedy algorithm is somewhere over here, in terms of time, you can, make this much, much faster at a very, very small drop in the function value. Okay. And even, a way to make this even faster is kind of function specific. And this is where you use the idea of memoization. So the idea is that to compute the gain of the function, you can use certain precompute statistics, right? And that way you can achieve even more speed ups with the help of this precompute statistics, right? So in fact, for several functions, you can maintain various precompute statistics, right? And this oftentimes saves the cost of evaluating the function from order n square to order n. Okay, so there's a large, gain with this, right? So you have, without memoization, you have the time, and with memoization, you have the time, right? So you can see over here that even with a million size data set, you can run this for various functions, and the time taken is, a few seconds, it's hundreds of seconds, right? For even, several million examples. So there's a library called Submodlib that is based in C++ that implements, several submodular functions. This was actually, built by one of my students, Vishal Kaushal. So please take a look at this. We are, adding several functionalities to this library. So, yeah. All right. So with this, I'll hand it over to Abir, and, Abir will cover neural submodular functions. So this will wrap up, part 1 on the theory, and then we'll talk about the applications. Any questions till then?
Oh, sorry.
Oh, yeah. Yeah.
So I was wondering, how strong a role does monotonicity play in the algorithms that you said, that if I remove monotonicity without the cost?
Yeah, that's a great question. So I mean, in the interest of time, I didn't cover a lot of that. There are a lot of specialized algorithms for non-monotone functions. They don't perform as well in practice. To answer your question about monotonicity, if a function is near monotone, right, a greedy algorithm oftentimes works well in practice. So for a lot of functions, because in the beginning stage, they are close to monotone, you can just apply the greedy algorithm, for all practical purposes. Yeah.
And also the guarantee that you showed in, I mean, while we cannot improve over the 1 - 1 over E or general submodular functions, I mean, I was wondering, there must be some guarantee that says that that kind of measures how close the submodular function is to a modular function.
Yes.
And based on that, it becomes close.
Yes. So there's a curvature. Right? Yes.
There must be something like that.
Yes. There is. So there is a curvature based guarantee, right? And that curvature based guarantee becomes 1 if a function is very close to a modular function. If a function is modular, is exactly 1.
Thanks.
Yeah. Thank you. Great questions. Okay. So I'll repeat the question. I think the question was, we spoke about mutual information and conditional gain. So what is the practical benefit of conditional gain, right? Where those are applicable? So it's a great question. So we'll actually be covering the second part. I'll be talking about active learning, and in fact, a framework of active learning called guided active learning. And over there, we'll see a number of applications where we will use the mutual information, the conditional mutual information, and the conditional gain function, mainly for, taking care of, for example, redundancy, out of distribution data, outliers, targeting to specific classes, data discovery, and over there, we'll actually see how, each of these functions are useful. So one specific example is data discovery. If you don't know certain instances in your initial labeled set and you're doing active learning, right? How do you discover these instances without any information, right? So it turns out that by conditioning, we can actually condition upon the existing labeled set and find instances that are, dissimilar to the labeled set, right? And we can use that to actually discover new classes or new slices that your model is blind to. So we'll actually cover those applications. Yeah, but great question. Any other questions on this part? Okay, so with this, I'll hand it over to Abir. So Abir will cover, the second part of part 1, and then we'll move on to applications.
Hello, am I audible to the last? Oh. Okay. Hi, thanks Rishabh for a very comprehensive introduction. So here I will talk about how to design neural models for submodular functions. So to start with a motivation. So why this goal? Because as Rishabh described, that it has a good use in diversity and representation. So using a single function, you can model both diversity and representation in one way. So for example, look at this function, which is a graph cut. So the first term sort of indicates that you are trying to select a set S that has high similarity with other elements or the total elements in the universal set, that is V. Okay. So basically it kind of encourages, if you try to maximize this quantity, this term is trying to encourage that S that kind of represents the entire V, because you are trying to maximize in this dot product, which is a measure of similarity. So you can use other kinds of similarity functions as well. And suppose you take a lot of instances as a member of this S, so then it can happen that you are repeating one again after another. So this term is trying to penalize the self-similar items. So suppose you have selected one item, similar to that item has already been selected in the S. So you try to penalize this quantity by a factor sigma. Okay. So this Fs is a good function that characterizes both diversity and representation. So diversity is indicated by the second term and representation is indicated by the first term. So due to this, submodular functions are often used for data summarization tasks that Rishabh has already mentioned. For example, if I give you a set of images, then it's very likely that, you know, if you want to find a subset of images that represent the entire set of images, okay, you are going to compute, use facility location, some kind of information measure, as Rishabh has pointed out, to select the subset. And they are often submodular. So naturally, the idea is that, you know, different submodular function kind of characterize different set of representation, different type of representation and diversity, so that by given the data, can we learn the underlying submodular functions? Okay. So the idea is that suppose I give you a set of instances, okay, let's say xi and yi's, okay, and then we wish to learn f from the subset to R, so that y equal to fs. So S means a subset of i's in the data set. So you take a subset of data sets and you want to learn y equal to fs. So you are given just an element, set of elements and the corresponding y. Okay, so that this is submodular, so that, you know, we can characterize this well. So from the definitions, so I will try to describe that how we can construct various neural models. Okay, because remember that you have to come out with a generic submodular function, okay, that will be able to satisfy this. And at the same point of time, for different values of the parameters, it should give different types of submodular functions. Okay. So basically you have to find a unified nonlinear submodular function. Just think about neural network. So if you make a complex neural network, if you build a complex neural network and you try to train on the data set, the idea is that it should be able to capture any kind of nonlinear function that is running on the background to generate the true data. Okay. So exactly this is the idea. Suppose you generate y, the ground truth, using facility location, or you generate the ground truth, let's say, for example, using graph cut or like log determinants, or various type of submodular function. Okay. So, and you don't know that function. So how you learn that? Of course, if you assume that it's a facility location or like graph cut, you can try to learn the similarity functions. But suppose I don't specify the type of submodular functions that is running on the background, or that's the underlying generative submodular functions for producing the data, then you cannot make any assumption. And for that, you have to develop a neural model for that. Okay. So here the idea is that I want to learn a submodular function. So that means I want to find a neural model which will satisfy this condition. Okay. So the point is that the submodular function satisfies this condition. So looking at it in a different viewpoint, if you look at the marginal gain, that is ft union e minus ft, this is decreasing. Okay, that's the signature of submodular function. So now we have to find some nonlinear form of f, a very expressive form of f, high capacity neural model for f that satisfy this property. Okay, so how to do that? So constructing set function is always difficult, right? So there are deep sets, set transformer, but they're very small in numbers. Like if you think about continuous valued neural networks, there are plenty. Convolutional neural network, LSTM, feed-forward and everything. So it's very easy and intuitive if you translate this problem in a continuous space. Okay. So designing a set function is difficult. So we'll think like, how can we move from continuous neural network, like continuous valued neural network, to go to the set valued neural network that satisfies this condition. Now, can someone think of a continuous analog of submodular function? So there is a kind of function we observe daily in practice that's kind of reflects the similar kind of nature of this submodular function of submodular function like this. So what is that? So this is the question specifically. So what is the type of continuous function which is the closest analog of submodular functions? So the idea is concave functions. So why that is the case? So look at the concave functions. So the concave functions looks like this. The double derivative is basically this quantity. That is, you take the derivative first, you just make the difference between first derivative and divide by this infinitesimal quantity. Okay. And look at this point that it is less than 0. Right? So you can think about this is Ft union E and this is Ft. Okay. So if you make this difference, this is less than 0. So basically concave functions, in the concave function, you have like, if you increase x, it will decrease the value of x, the gain of x. So that means that if this is the gain in the continuous function, for the continuous function space, the first derivative is essentially the gain of that function, right? If you just increase x, what will be its value? So this change is, or this gain is kind of negative. So if you increase x, then the gain is negative. Okay. Similarly, in submodular function, adding element decreases the gain of f. Correct? So that is the idea. So can we use concave function to model submodular function? So let's say I will use submodular function, concave function first, and then use that concave function to model the submodular function. So the basic idea is that I will just try the simplest form of submodular function, which is called modular function. Very simplest, the most simple form of submodular function, and then apply concave function, and then it will be submodular. So basically, this is like this. So start with a very simple modular function like this. So it has to be positive. So all the values of mxi has to be positive, and then this quantity you just pass with it monotone concave functions, and it's guaranteed to be submodular. Okay. But moreover, since f is monotone and this quantity is positive, this m is positive and f is monotone, this is also a monotone submodular function. So now, by using this mechanism, one can recursively construct the submodular function by this manner. So you first apply your f1 and then apply an f2 and so on and so forth. And then you can recursively wrap these modular functions with one after another to sort of generate the submodular function. So that's the idea. So any questions until this? Okay. So using this mechanism, there is a paper in NeurIPS 2017 which does exactly same. So they kind of start with a very simple modular functions and then apply a concave function, add again a modular function, then apply another concave function, and you can increase the depth of the neural network by just applying more and more concave function in a recursive manner. And then you get a very powerful model of concave function. And if you try to learn from the data, so it will be able to learn whatever submodular functions you have been able to do. So for example, for some specific instance of concave functions and the modular functions, you can model phase relocation and then graph cart and so on and so forth. Okay. So what they specifically do, they fix these functions. That means the concave functions are fixed, and then just do model the modular functions using a neural network. So that means that the set of parameters is actually limited to only the modular functions. Okay. So that means that you just try to construct a positive modular function, like pass every x to a positive function. Okay. Add them over the set, pass it to any concave function. Let's say log, let's say square root, or any kind of concave functions, and then you sort of get a submodular function back. But that is a low capacity. This is a low capacity network because it only trains the modular functions. So it does not parameterize the concave functions as such. And since the concave functions are kind of set a priori, it kind of limits the capacity quite well. For example, suppose you generate data using square root. Okay, and then you kind of apply modular functions, okay, and then apply a log on top of that and try to learn square root from log. So it's not going to learn. So we have seen that. So basically, or in other words, if you just let's say apply logarithm to generate the data, but when you learning, you are basically using square logarithm or like square root, something else to learn the underlying parameters. It's not going to work. So it kind of is constrained by the strong assumption of the underlying concave functions. Okay. So what is the way out? The way out is to train a neural model for concave functions. So we have to provide a neural model for concave functions. So this paper, the set of papers like by by and Billings on 2017. So they assume the functional form of the concave function, and that limits the capacity. So we need to train a neural network which will be able to learn the underlying concave functions. So that's here is the task. So how can we give a neural model or some generic model for concave functions? So it just, if you apply your class 12 knowledge, so this is the idea, right? So you just do a double integration. So just take a positive neural network, take minus out of this, and just do the double integral, and that's it. You are done, right? But there is a problem. Can someone identify what is the problem with this function? So over to the house. So what's the problem with this function? So look at this line and this line. So what is the problem with this function? This is certainly a concave function because the double derivative is negative. Now, what is the other problem for which this will not work? Is it increasing? You take the first derivative. You take the first derivative. It's 0 to x minus h a dA, and it's negative. So the first derivative is negative, so that means it's not increasing. So we need to construct an increasing concave function. Okay? So this is a problem. So the first derivative is negative, the second derivative is of course negative because it's concave. So this is not going to work for us. We do need an increasing concave function. So what's the way out? So the candidate is this. So we don't take the first derivative from 0 to x, but we take from a to infinity. So by doing so, and this h theta is positive. So if you notice this, the first derivative is positive, the second derivative is negative. Okay, as long as you make h theta b to be positive. So now that's the idea. Like, now what all you have to do is that you have to translate, or you have to model this h theta b using any positive neural network. And not only that, so apart from submodular function, this kind of network is of independent interest because it's a universal approximator of any concave functions, any increasing concave functions. So that means if you give me any real concave functions and with the data generated from that, theoretically it can be shown that I can construct a neural network with enough depth and enough breadth so that the difference between fx and the function that you provide, that difference is less than epsilon. So basically, all you have to do, you have to just give any complex neural network, consider any kind of complex neural network, any universal approximator of any function. So ideally, what I prefer, when I code it up, I find that linear, ReLU linear. So if you just cascade this kind of network, they work very well. So that comes from a theorem from 1991 that you are plugging a discontinuous function between two linear networks, and that's why you can model any function in the universe, okay? And therefore, let's say you just feed a linear ReLU linear on top of that and just apply a ReLU on top of this. So G theta can be any universal approximator, any kind of complex nonlinear function, and just apply ReLU on top of that. Then it will give you a universal approximator. This final fx will be a universal approximator on any concave functions. And we have shown that this kind of function, if you use to model the submodular function, it works quite well. And it gives some kind of guarantee for a subset of submodular functions. Okay, so to see the empirical results, so there are 4 functions, okay? First function is that flex subnet that I have just shown in the previous slide. The second one is set transformer. That means that you perform all kinds of interaction between element subset. Third is the famous dipset function. I mean, it's just, you add the elements of the set and, the vectors of the S and, pass through a neural network. And the final is the DSF, where the concave functions are fixed. So if you look at the numbers, so the first point that I want to make, that if you give set transformer enough capacity, it's going to beat any function. So we have seen that. It's going to beat flex subnet, it's going to be deep set, it's going to be DSF. So set transformer is an outstanding set function. The problem is, even with, we have checked it, even with like order of 30 parameters, it's going to consume 16 GB GPU. So you just reduce the depth and the breadth of the set transformer to reduce its parameters, the set of parameters as 30. Okay. So it's going to consume 60 GB. And that too in a reasonable batch size. And if you increase, the set transform, the size of the set transformer more and more, you have to decrease the batch size because otherwise you see memory error. And interestingly, what we have seen is that even in that paper, the set transformer, what we have seen, they have mentioned that, they could not go beyond elements of, the universe said beyond 1000, because beyond 1000, they could not load it in a 24 GB GPU. So that kind of reassuring that, it's very costly in terms of the memory to implement deep set transformer. Secondly, none of the other model, flex subnet, deep set or DSF, they are considering interaction between elements. So what flex subnet is doing? They are just adding the elements in terms of the modular function. So basically they are adding mx1, mx2, mx3. Okay. You are not computing product of x1, the interaction between x1 and x2, x1 and x3, and so on. So none of this model actually computes interaction between sets. So it's bound to fail. So to make a fair comparison, what we have done, we have maintained the size of parameters in such a way that with the same batch size, they consume same amount of memory. So with that, we have seen that this kind of model perform much better. In fact, this DSF, we have seen DSF to perform poorly. One of the reasons is that, the misspecification of the concave function. So basically, suppose you basically, let's say you generate the data using log, okay? So just log of modular of x and it's a concave function. So what happens now when you are going to train the f theta s, you underline the concave function, the functional form that you assume, if it becomes square root, it's not going to fit well. That's exactly what we observed here. So even if the fact that, DSF is a model that explicitly characterizes submodular function, since the concave function is misspecified, it's performing worse result than methods like set transformer or deep set, which are not specifically designed for submodular functions. So that's one of the key observations. So from set transformer, what we have learned that interaction between two elements are kind of very important. And so an interesting future work here is the, designing interaction-based model for submodular function. And that's really difficult because, there is no such relation between continuous space function and submodular functions that can tackle this interaction. So this is an open area of interest. So yeah, so that's all from me for the time being. Before I hand over to Rishabh, so I'll request if you have any questions, you can ask. Yeah. Any questions from the audience? Log, square root, sigmoid, as long as the argument is positive. You can take all possible concave function, but okay, so this is one important point. So we got some feedback from some conference. Why didn't you try with a lot of concave functions? Theoretically speaking, or like in the history of neural network, everybody says that your activation function is fixed. It will be ReLU or it will be sigmoid. What you should search over the depth and breadth. But suppose you are also allowed to search over the activation function, then I don't think the universal approximation or the sense, the results of universal approximability holds true because, then you only need one layer or one layer neural network, right? So basically you have just, suppose I generate a complicated functions, okay, using fx, let's say f is some very, very complicated function. And I ask you to search over all possible functions, then you will just end up searching over that function that generates the function, right? So in the tradition of neural network, everybody says that keep the activation function fixed, either sigmoid or ReLU. Search over the depth. You can increase the depth, you can increase the weight because that's searchable. It's a polynomial operations. But if you are allowed to search over all concave functions, yes, DSF is much better, but that is practically impossible because the number, there is no space of fixed concave list of concave functions. So I kind of tried with log, sigmoid, and square root, and this did not give good results. But if you go for beyond that, log plus sum plus square root, or 1 by x to the power 1 by 4 for some regime and log for some other regime, yeah, that can work out. But the problem is that, it's much difficult than hyperparameter tuning. You are searching over the space of functions. Yeah.
But these are all taking a lot of data.
For our case, it is not. It should not take a lot of data. So, okay, to give you a clear statistics, we worked with our training set consisted of 3,000 data points, which dimension 100. And we are being able to learn until as function as complicated as graph cut. So we have been able to do that with two-layer neural submodular functions. That means, if you look at this, just 1 second. So here, if you look at this function, concave, there are k layers, say for example, we just limited our setup with 2 layers, a concave and concave. And then we tried to with 100 dimension elements with 30. So each set consists of maximum, let's say 3,000 elements, and it's being able to perform well. Of course, it's a little bit slower than DSF because you don't have the overhead of training concave functions there. But it's much faster than set transformer. But yeah, I mean, it's being able to train well. So there are some training issues that we have encountered, but fixed that. For example, for some corner cases for, let's say, the initial problem, it was not converging. But once it, after 5-6 initialization is very, you will be able to find some conditions. So there are some nice initial conditions that can give you really, really good error, like low error.
So yeah, I'm just curious, what would be some of the practical applications of something like this? I mean, so you would expect that in comparison to fixing the submodular function, this should show better performance against certain metric.
So good point. So basically, if you look at, let's say, this paper of mine, like in this new RITS paper. So one important application of learning submodular function that I did not mention because of the time is that summarization. Let's say in the recommender system, you are given a person or a set of items, okay? And you don't have any information, let's say from the completely privacy preserving viewpoint. And then the person, buys a subset of that items. So you can think that given the set of this universe, the subset of items the customer has bought is a good summary of that overall thing. Okay. So now the problem is much more challenging. You are not given the pairs of S and Y. Correct? You are given a subset, you are given a universal set. That is the overall set of items and the subset that the person has bought. Which means you can think that as an instance where you are given a set of items as universe V and the subset that maximizes the submodular function. So this is an extremely weak supervision. And we have shown that this method performs well there with respect to other methods. That's in the paper. I have not shown it there. But the answer is clear. So basically you are given a set of universe and I give you only one set. Okay? Which represents the set that gives the highest value of that function. Okay. And I give you many such pairs like S1, V1. For one universal set, this is the argmax or like the value of the set S that maximizes the submodular function. Another V2 and the corresponding S2, the high value subset. Another V3 and another high value subset. And I give so many pairs and you'll be able to learn this, but it needs a lot of samples, yes. And there is a, thankfully, so we have been able to publish this paper. Thankfully, there was a NIPS oral, which specifically designs for even non-submodular functions, how to learn from, high value set. So that got a NIPS oral, and that gives actually much better performance. But that model is not limited to subset, and that is a very specialized thing for any kind of set function.
Okay, thanks.
This might get a little theoretical, but I mean, I was wondering that do you know or do you believe of that? Suppose I'm thinking of low complexity submodular functions. I mean, complex submodular functions, I don't know. Now, do you think that there are families of such submodular functions for which, and I'm thinking of a setup like this, that I give you examples of S and f of S, and where fs is the, and I give it to your model. Right now, will your model be able to always reconstruct f of s on the unseen sets, or do you think that there are families of submodular functions in which it does not do it does not get close? You have a sense of that, or
okay, easier. So exactly. So let me be specific. So exactly, this is something that it is happening there. But is your question specific to the context where, let's say I give you a set of S and Fs, but the universe is not revealed, like the boundaries is not revealed. Like, good question. Yes, actually I have seen, but better than the baselines. But suppose you mention one boundary point that, let's say you mention one high value of S, like, let's say like x1, x2, xn, you mentioned. For some boundary, at least in small quantity in the training set, that helps. That's what I observe. So basically, you mean to say what I have understood from your question, you are more or less asking that if there is a universal set, and let's like rank the items based on their numbers, right? Like say x1, x2, x3, you just sort them in some sense, and then take the first k element, and the trainer doesn't have an idea about the universal set at all. That's your question, right?
Oh, not exactly. Maybe we'll take it offline. I think that's better.
Okay. Okay. So now I will hand over to Rishabh for the first part of the application, which is about active learning.
Okay. Can you hear me? You can hear me, right? Okay. So just stepping up a little bit, right? So the first part, between me and Abir, we covered what submodular functions are, right? What are the modeling capabilities of submodular functions? What are the optimization algorithms, right, that we can use to optimize submodular functions? And finally, neural submodular functions, where you can learn submodular functions for your applications, okay? So, I'd like to point out that in terms of applications, there are probably, 10 to 15 domains where submodular functions, combinatorial optimization have been used. And obviously in 1 hour, we won't be able to do justice to all of them, right? So we are going to talk about 2 specific applications, right, which are somewhat related. So we are going to kind of only focus on human in the loop learning. One is active learning and one is human assisted learning, right? But I do want to mention that there are many, many other applications. There are applications in compute efficient learning, where you can, select subsets of data points to make training more efficient. There are applications in data summarization. There are applications in recommendation systems. There are applications in search. Obviously, active learning, human in the loop learning, so on and so forth, right? So there are applications in many, many areas, but we're just going to kind of cover a few of them. Okay. So again, right? So a lot of applications of subset selection in, deep learning, like massive data sets, massive compute. We are going to focus on the active learning aspect. Okay. So from an active learning perspective, kind of the way to think about it is, in some sense, you can say data is all you need, right? But really it's the right data is all you need, right? So the goal of active learning is really to find this right data. Okay. So how many of you are familiar with active learning? Or rather the inverse question, how many of you have not heard active learning at all? Okay, so some of you. Okay, so don't worry, I'll give you a high, brief intuition of what active learning is. So active learning has been, one of the oldest fields in machine learning today, right? Because active learning ties in with one of the most important aspects of machine learning, which is getting labels, right? So machine learning, supervised machine learning requires labeled data, okay? And the way you can get, one way you can get labels is by actively seeking labels with a human in the loop. So I'll show you, how this is. But this is the basic paradigm of active learning, right? So you have a human annotator, right? So in any machine learning task, you need humans who can label, right? So you have a human annotator. But instead of giving a human, a million points to label, you can do this in an iterative manner, right? So you have an unlabeled pool of 1 million data points, right? You use a machine learning model to tell, a human which subset of the unlabeled points will be most informative for the model, right? So a human can label that and essentially do this in a loop, right? So that's the basic idea of active learning. And a lot of paradigms are there for active learning, like entropy, margin, least confidence, badge, a bunch of approaches which are, related to combinatorial optimization. So I'll talk about them very briefly. So, so this is the loop of active learning, right? So you have a human labeler, right? A human labeler basically, so active learner will take the unlabeled data, right? And then will basically specify unlabeled data points. So this is where the active learning algorithm comes in. It gives unlabeled data points for a human to label. A human labels the data points, right? And then these data points are provided to a machine learning model. A classifier is trained. And this classifier is again used by the active learner to then select more unlabeled data points. And this continues in a loop. Okay. So standard approaches for active learning are uncertainty based, like margin, uncertainty, least confidence, right? They do not model any interaction, right? So one takeaway that you must have seen is submodular functions capture things like diversity representation, right? So if a human has already labeled one image, you don't want to give a very similar image for a human to label, right? Why? Because it's not needed, right? They have already labeled something similar, so the model can learn from that. So diversity and representation obviously are very important in active learning, and most state-of-the-art active learning approaches use them. Okay, so active learning consistently has demonstrated 2x to 4x improvements in labeling efficiency. Okay, so most work in active learning focuses on diversity and representation. Okay, and broadly speaking, I'm listing a few papers over here. I'm not going to go in all the details. But all of these functions use some variant of something related to a submodular function. Okay. So this paper, which was actually our work from 2015, uses a facilitation function as a submodular function. This work, which is a 2020 work in ICLR, many of you must have even used this approach. It's an approach called badge. This one uses, takes gradients and uses a diversity function. So in fact, it uses a log determinant or a, DPP, right? So it's a log determinant function. So this is also a submodular function, right? You have core sets, which is robust case center, batch bald, which is a mutual information function. So all of these use variants of combinatorial functions for finding, the subset of data points to give for a human to label. Okay. Any questions until now? Okay. So what's broadly speaking the active learning framework, right? So if I have one slide that I can summarize most approaches, it will be a flavor like this, right? So I have an initial labeled set L, a large unlabeled pool, right, of data points not labeled. I have a model M, a batch size B, and a number of selection rounds, right? So this is a number of rounds of labeling that I will perform. So I iterate here from round I from 1 to N. I train or fine tune the model M on the current labeled set. I use this model to compute a similarity matrix. So it's a pairwise similarity matrix, right? of similarities of all samples in U, right? Either using features or gradients. And then I instantiate some kind of a set function, right? Either a log determinant, minimum dispersion, facilitation, robust case center, clustering, some form of a set function I initialize, right? I maximize this to obtain this set AI, right? I get the labels of, this set AI and I iterate, right? Once I get this, I increase my label set, I again fine tune the model and repeat this. Okay. All right. So this is a performance of active learning on several data sets. You can see that it's consistently better than random sampling, right? So from a labeling efficiency perspective, the labeling efficiency, you have around 2x to 4x labeling efficiencies compared to random sampling. Okay. So the focus of this talk is actually looking at how we can go one step ahead and use the framework of submodular information function that I spoke about, in the theoretical section, how we can use this framework for actually applying to active learning in real world settings. Okay. So the real world data setting is challenging, right? Why is it challenging? Imagine that you have different shapes over here as different classes, right? And you have different colors as different slices, right? So a data set like this, right? You have imbalance at various levels. You have imbalance at slice level, imbalance at class level, right? So some classes may be rare, some slices may be rare. So for example, if you have an autonomous driving use case, you could have, foggy instances which are rare, rainy instances which are rare, so on and so forth, right? So the major problem is you have imbalance in classes, right? So for example, look at autonomous driving. This is actually a case where a Tesla went and hit into, one of these bollards over here, right? Green color, because they were trained for yellow color bollards, but they couldn't recognize green color bollards, right? So Tesla went and hit this. So this is just one example, but you have rare classes coming up all the time, right? So look at a medical imaging data set like this, you will have some kind of a skew in terms of your classes. Okay, you will have rare slices, right? So you have autonomous driving, you have motorcycle at night, you have foggy weather, you have rare classes like this, motorcycle and bicycle, you have rare slices, which are motorcycle at night, bicycle at night, right? In the case of speech recognition, you have various accents which are rare. So rare classes and slices are everywhere today in machine learning tasks, right? Another challenge with real world data sets is outliers and out of distribution data, right? So think of medical imaging where you are used to seeing certain kinds of images, but you could have incorrectly acquired images, right? So you could have lateral views, rotated images, underexposed, incorrectly cropped images. These are all, by the way, real world challenges in many of these tasks, right? Another important issue is redundancy, right? A lot of real world data has a lot of redundancy. So all of these are issues with active learning, right? Or actually any machine learning task, but I'm going to focus right now on active learning, right? Because active learning today is a very useful tool by which you can get labeled data, right? So how to perform active learning with all of these issues? How do you perform active learning with imbalance, with outliers and out of distribution data and redundancy? Okay, and how do you also personalize to specific distributions and slices? So we're going to talk about a guided active learning framework now, in the next several slides, and we're going to see how we can use these submodular information functions, right? So the first application that we're going to talk about is active data discovery. So what's active data discovery? Imagine that you have a set of, say you're trying to detect, do number recognition, right? So between, digits, handwritten digits. And most of your data set comprises of zeros and ones, right? But you have certain rare instances of 2 and 3 that you're not aware about, right? So your current labeled set does not have any 2s and 3s, right? So the problem of active data discovery is how do you use active learning to actually discover these rare classes? Okay, so it's a subset of active learning problems where you assume you do not even have, certain classes in your labeled set, okay? Another application is targeting or personalization, right? So if you know a certain subset is rare, like say 2 and 3 are rare instances, how do you target 2 and 3 so that you can sample more and more examples of 2 and 3, right? And finally, you might have some out of distribution data, right? So you have in a digit classification case, you might have some alphabets, right? So how do you filter out some things that are not useful for your task, right? So how do you filter out outliers, out of distribution data, and remove redundancy, right? So this is the full picture of guided active learning, right? Where you want to do exploration, you want to sample, with unknown rare slices, you want to do data discovery and targeting and filtering, right? So this entire framework is what we call guided active learning. Okay. Any questions?
It's a diversity representation.
Yes. Okay, yeah. So I kind of went over this in the first part, but I'll kind of cover this again. No. So I'll cover this again, right? So the basic idea of diversity and representation is, imagine you have a set of points, right? Something like what clustering does is it clusters points into groups, right? And then you have a representation from each group, right? A representative point. So this is called representation, where I pick one centroid from each group, right? Diversity is something where I pick points as far away from each other as possible, right? So if I just sample based on diversity, I can sample a lot of outliers, right? I can sample points that are as far away from each other as possible. Whereas with representation, I will only sample points which have some mass. I will avoid the outliers. So that's the basic difference. So certain active learning approaches, right, have been built based on representation using, say, festival location, right? But many of them actually use log determinants, right? But we'll see that actually the case of certain applications, like for example, out of distribution data, log determinants may not be as good. Okay. So there are several, interesting kind of motivating applications of our work over here. So, a lot of these applications of guided active learning stem from things like medical imaging, autonomous driving, personalized machine learning, wildlife monitoring, ecology, text classification, so on and so forth. Okay. So broadly speaking, the guided active learning framework is where we will use a well-designed query set and a conditioning set to actually then, use in the active learning framework. So if you remember, everything in active learning is the same, except that here we are, instead of optimizing a submodular function or a set function, we are optimizing a variant of a submodular mutual information function, right? So I am going to select something related to a query set. A query set could be a rare class or a rare task or a rare slice, right? A set P over here could be a conditioning set P, could be something I want to avoid. So it could be, for example, redundant data, right? Or it could be, a label set if I want to do data discovery, right? So different instantiations of active learning would use different variants of Q and P. So we'll see some of these. So let's start with active data discovery, right? So again, recall, active data discovery is where I have a certain, set of classes here, and I'm trying to discover new classes that are not present, right, in my data set. So imagine here I have my seed labeled set, right? But a lot of classes, in fact, this class is not even present in my seed labeled set. Okay. So how do I do active data discovery? I just this is where I use conditioning, right? So there was a question earlier that how do you use conditioning? So here you use the conditional gain function and you maximize the conditional gain of A conditioned upon L. Okay. And once you sample the rare classes, you can then target on those classes. Okay. So this is basically active data discovery, right? And we can see with the results that active data discovery actually discovers the rare classes and the unknown samples, unknown classes much faster than existing active learning approaches. Okay, so this is active data discovery where you want to discover classes or slices that your data does not have right now. Okay, any questions so far? Okay, so the second aspect of active learning is where we'll do targeting and personalization, right? So imagine you have found using active data discovery, you have found two slices or two instances here, 2 and 3, but you just have one example of 2 and 3, right? So how do you boost the number of samples of class 2 and class 3? So these are your rare classes, right? So the goal here is to target, using the query set here, you can target classes 2 and 3. You can target instances of 2 and 3, right? So again, this is just a repetition of what we had earlier. This is also useful in actually object detection, where you know your query task is, say, motorcycle at night, and you want to basically boost up the number of examples of motorcycle at night or bicycle at night. Okay, so this is our work from ECCV this year, where we actually came up with a framework of targeted active learning for object detection, right? Particularly with autonomous driving, where you have certain rare classes and rare slices like motorcycle at night. And how do you get more samples of motorcycle at night? So the basic idea is I use as my query set, instances of motorcycle at night, and then I, do this targeted similarity and optimize this targeted mutual information. Okay. So we see over here that, this performs very well. This is results of CIFAR-10, MNIST, standard data sets where you have some rare classes, right? So on the rare classes, we have significant gains. So for example, we have almost 10 to 18% gains in terms of average accuracy on the rare class. And in the case of medical imaging, again, we have certain rare classes. These are medical imaging data sets. Again, we see similar performance. And finally, in the case of object detection, we look at various rare slices like motorcycle at night, bicycle at night. And again, we have significant gains, almost 5 to 15% gains in average precision on the rare classes, right? On the rare slices in this case. Okay. So this is the use of targeted learning for actually improving the performance for rare slices, right? And rare classes. Okay. There's some qualitative results, by the way. So you have an object detection here. This was trained, or with very less data with night, because the BDD 100K actually, if you sample a random subset, it will have very less night images, right? So after targeted learning, you see the performance improved, drastically, right? Okay. So the last part of this is where we want to filter out certain instances, right? So either we want to filter out outliers, filter out of distribution data points, or redundancy, right? So again, looking at our toy example, right? If the blue set of points here are like OD out, the blue set, these points are all, outliers that we want to sample out, right? And the red sets are all redundancy, right? So how would you use, the notion of conditioning to actually filter out of distribution points and diversity? Okay. So the first is redundancy, right? So we can achieve this by, further again, conditioning on the labeled set, right? So that way we can achieve a set of points A that is diverse with respect to itself and diverse with respect to the labeled set A. Okay. So there's a slight difference between active data discovery, because the goal of active data discovery is to, find outliers. Okay. So you actually would use a larger width of a kernel, right? In this case, whereas the goal of redundancy filtering is actually to ensure instances in close proximity are not selected, right? So you use a smaller width of kernel. So there's a slight, difference between the two, but at a high level, both are somewhat similar. Okay. So again, using redundancy, we see that, if you do active learning with a lot of redundancy, using conditioning, we can improve the performance. Okay. Finally, this is diagnose with the application of medical imaging, where you have some, you have some out of distribution points, right? And here, what we are doing is we are using this mutual information function by finding the subset A related to this in distribution points, while conditioning upon the out of distribution points O. Okay. So you will optimize this mutual information function, right, in this framework over here, right? And we actually consider several classes, several kinds of, several scenarios with different difficulty, right? So the first is somewhat easy, where you have unrelated images, right? So if you have, medical imaging data set, right? But you have some out of distribution data of completely unrelated images. Okay. This is arguably an easy case, right? The slightly harder case is where you have correctly acquired images as your in distribution points, but incorrectly acquired images as out of distribution points, right? And finally, you could have different views, right? So you have the axial view, right? But you have different views like the sagittal view or the coronal view or mixed views but you only want to do your classification on the axial view, right? So you're going to have different kinds of out of distribution data in your unlabeled set, right? And by the way, all of this is like very natural use cases for doing active learning in real world applications. Okay, so we did several experiments, in collaboration with a group, with medical imaging folks, and we saw that, our approaches, give significant improvements in performance, right, for various data sets. So this is simple CIFAR-10 data set, but this is with various, dermatoscope, abnormal CT, axial, abnormal CT, and so on and so forth. So this is a scenario with unrelated images. This is a scenario with incorrectly acquired images, and this is a scenario with a mixed view images, right? And in all cases, we see that our approach can sample more number of in-distribution points. Okay, yeah. So, okay, so I just want to point out that, we have a toolkit here called Distill, which, has a bunch of active learning approaches. Okay. So, yeah, so maybe in the interest of time, I'll skip all of this, right? And hand over to Abir. So how much time do we have actually? Okay, so maybe, yeah, so sorry about that. I think we kind of lost track of time because we started a little bit late. Okay, so maybe in the interest of time, we'll probably skip the last part. So any questions on this? Or Abir, do you want to give a very, very quick high level?
So should I go in detail or like?
Just like maybe a 5-10 minutes summary. Sorry.
No problem.
Somehow I lost track of time.
No, it's okay.
Maybe we can take questions offline.
So how much time I have? Okay, so I will give a, I will give a very brief overview of this part of application, which is about human assisted learning. So it is more connected with what Dijotam talked about in the morning. So coming with a high level motivation. So I'm not going to talk anything about the last couple of parts. I will just give the high level motivation, and I will say how it is connected to the overall subset selection framework. Okay. So we are already much into artificial intelligence. So we have seen ChatGPT and everything. So machines are almost as good as human in some cases, but still societies are relying on human expert to take the final decisions. It's not about accuracy, but it's also about the responsibility. So a couple of years back, it happened that there was an accident by some autonomous car, and people don't know, like the law enforcement agency did not know which one has to blame for. The one who is the one who is written the code, or the manager, or in the part of the code that actually caused the bug. So it's not just accuracy. It's not about time. It's not about scarcity of resource. It's also about the responsibility. So this is because, at least someone to blame for if something goes wrong. So that's exactly why societies still rely on human expert to take decisions, which have significant consequences, like specifically medical decisions, and then hiring, law enforcement, judges, judiciary decision makings, everything. So, but timeliness and the quality of the human decisions are significantly compromised by two factors: large number of decisions and then shortage of human experts. Okay. So, of course, you can use machine learning to solve these problems. In many cases, as I have just started with the talk, machine learning models have surpassed the human performance in cases like recognition image, playing complex game like chess. However, they're sometimes worse than human. For example, here, so you can see at least in the 40% of cases that machine decisions are still worse than human decisions taken by human experts. So here is the question that, given a lot of training examples, or given a lot of features, like a space of features, can you partition the feature space, or can we partition the training samples in two parts? So one part will go to machine for the decision making, and the other part will go to the human. So the idea, so here you can think that you are training the machine learning model at different automation level. So if you ask the machine to take the complete decision, it's a full automation. The human is out of the loop. Now, if you ask the machine to take decision for 90% of the points, the question is which 90% of the points is going to take. So they will take the decision for a fraction of instances, and the rest of the instances are outsourced to human. Okay, so this is the main modus operandi. So is the motivation clear to everybody, or is there any question? Okay, so I'm proceeding. Okay, you just give me an indication where to stop. Okay, so let me talk about the full automation trash. What is it? So how to partition the feature space into two parts. So what's the most commonsensical ways? You basically train. So the idea is that you basically train the machine with all examples and check where the machine is performing poorly. So basically what you do, you train all examples here, as you can see, with a linear line. Suppose you want to fit a linear model, and then observe that what are the points that machine is performing poorly, outsource them to humans. For example, here at these points, machines are not that good at this blue point, so you outsource them to human. So if you write a pseudocode, it's just like, sort the examples in the decreasing order of this and outsource them to humans. Okay. And how to test on the unseen examples? Because you have to compute the error or both human and machine. So for computing the error, you need the actual levels, which is not available during test time. So you have to train an additional classifier to make that decision. Okay. So you train an additional classifier because in the train time, which samples you are going to, which samples you have outsourced to human and assigned to machines. So what you do, you basically add an additional classifier and train an additional classifier, which will give the output at, okay, this is going to human and this is going to machine based on this blue and red points only. Okay. Now there is a problem. So let me go to so there are other methods, but let me go to the problem directly. So the problem is that here the machine model is not optimized during training. So what does it mean? So during training, you never revealed machine that there is a human to take decision about. The machine knows that, I'm the person, I'm the entity which is going to take the entire decision. So it's not cognizant about the presence of human at all. So what happens that there are points like this regime, okay? Machine is performing in a very, very suboptimal manner. So it's the idea that, suppose you have a meta algorithm, which will tell the machine, hey, finally you are going to take care about this set. So that the machine would not have been trained on the rest of the set. Machine should completely ignore the rest of the points and would have been trained on this particular line only. And then the performance of this line will be extremely good. But now, since the machine does not know that there is a presence of human, or in other words, you did not actually specify the problem clearly to the machine, hey, there is a 90% of the points you can have to take care of, for the 10% of point you can ignore. So machine is kind of taking care of all points. And finally, it ends up that if these red points would have been assigned to the machines, then it could have performed much better if it is alone trained on these points. So if these points are the only points, these red points are the only points which are used to train the machine, then the performance would have been much better. So the key idea is that make the machine aware of the human. So what we do, by some meta algorithm, you kind of guess that these are the points that are going to be outsourced to the human, outsourced to the machine. Then the machine will completely ignore these points and will be only trained on these points. So just give a simple analog. So suppose I ask you that you have to do good in, let's say, math and physics. Okay, and you don't have to do well in history. So we'll just prepare for maths and physics only. Okay, but if I don't reveal, and finally the marks is considered only based on maths and physics, then your performance would be suboptimal because you have spent time on history, geography, and other things. So this is exactly what is happening. So that you basically guess at what point machine is good. So if your strength is at maths and physics, I say that you just only take care about that. So our task is to kind of guess what the machine is good at. So this is where the subset selection comes into play with the overall framework, that let's say this is the human error per sample. And let's say this is the portion where machine is good. And I don't know what is S. So along with the machine model, I'm trying to minimize also the S, the set of examples that are, that are kind of to be found out. So basically the optimization variables are not only W, but also S. So now you observe that W is being trained only on SC, the complement of S. So it's not being trained on the entire sample. But by solving this optimization problem, I'm automatically finding which S or which S is to be, which is optimal, or which are the points that given the presence of the human, machine is good at. So make machine cognizant about the presence of human, number one. And given the presence of the human, given the level of the performance of the human, you automatically find the strengths and weakness of the machines. That's the idea. And so this kind of reduces to the subset selection problem. And for the interest of time, I'm just skipping the methodology. It's just a, some kind of greedy algorithm. So this, you can use some kind of greedy algorithm to get some approximation guarantee. So you can look at the paper later on. So do you have time? No. Okay. So okay. So just give you an example where it is doing good or doing bad. So, so this is an easy example. Okay. So you can see that there is two photographs. So one photograph is about Duchenne disease, which is characterized by pathological yellow spots. Okay. So apparently, this point, it looks like a Duchenne disease because it has yellow spots, but somehow machine rejects it because it turns out that it is not actually Duchenne, but it is related to diabetic retinopathy. So machine automatically finds that it's a difficult sample, so it's kind of rejects and sends to human. And for the easy samples, machine takes care. Okay, so that's it. So for the interest of time, I am skipping this part. So for the first part, or the overall motivation, if you have any question, I can answer for 1 or 2 minutes. Okay. Yeah. Okay. Okay. Oh.
So in the subset selection problem, when we are only focusing on the red points, which you highlighted, are we missing some information for the blue dots? I mean, now, are they going to suffer? So for example, the example which you took. So for example, the physics and maths. So my scores in physics and maths are less because I am focusing on other subjects. So now if I only guess that physics and maths are the points which I want to focus on now, and then I train the model only focusing on those points, then aren't my scores in other subjects going to suffer?
What are you, machine or human? Because this physics, so let's say that physics and maths are going to be taken by you. Maths and physics are going to be taken by you. For history and geography, there is an impersonator, let's say, who is going to give the exam for you. Okay. So that's outsourced to them. So you are going to only take care about the exams or the subjects that you are strong at.
Okay.
Okay. So for the points where the machine is weak, those points are going to be outsourced to humans. Yes, please.
Chance of catastrophic failure.
Yes, of course, because.
So what I'm asking, that isn't this a more unreliable technique? Means in search of human look, because you may miss something which is not humans.
Absolutely, absolutely. So basically, this is more like a foundational thing. I kind of agree. So there are 2-3 problems. I actually talked with Iyer in the morning today. So one is that generalizability of the human error. So it's very noisy. So it's not that for one feature, if the human gives one error, or let's say the human error is not Lipschitz. So if you part of the feature slightly, the human error will be also similar to the unpart of feature. So that's one problem. The second problem is that what I believe is that the scarcity of human annotations. So in principle, you should perform this in an active manner. Let's say you are not given Y, you are not given human annotation. You just perform the active learning methods. You search for one, give to the human, and then find at which area the human points are more reliable. Only for those points, you should outsource points to the human. So it's not about the error also, but the uncertainty in the error too. Yeah, here's some question.
So in the final loss function of subset selection, there was a component for human error also. So was that a learned model or?
Yeah. So, sorry. Okay, just 1 second. Yeah, this is the human error.
Yeah, is that human error, like, where is that coming from? Is that a learned model or?
No, it's given in the data set. Suppose you have an annotated data set where you can estimate the human error a priori. Say, for example, for one disease you have, for one challenging instance, you ask 5 doctors, okay, and then compute the expected error across all doctors. So that's a point estimate of the human error at that point.
So high variance points.
Huh?
High variance points.
High variance points means for
With
across
respect
five instances, yes, that can have high variance. So that's a measure of the error.
So should we give that to a
No,
human?
his point is that are we considering only high variance points? Is that your question?
No. So, okay. So my first point is like, how do we get that value
Yes.
for C of xi, y, because that's difficult to get. So
Yes.
you have to get that from human annotation.
But there are multiple cases. For example, let me give you one thing. So where it is very useful at, it's not in these 2 papers. So there was a 3rd paper called differential learning under trash. So they are galaxy pictures. And it's very difficult to really tell whether it's a star or a planet or something else. So you ask 5 scientists to do that. Okay. They give the annotation, like, there is a possibility that this is a star, this is a probability and so. And then from that, you can compute this C quantity across different people. So if you think that, all person has the equal expertise, right? Let's say, for example, and then these samples are kind of IID. The sample means is same as like, population means same as distribution. So that gives you the point estimate for that error.
Okay. Yeah. So my follow-up was that whichever sample is difficult for a model to predict upon, wouldn't that be difficult maybe for a human also?
For machine, what point is, so if the machine finds this difficult to
Maybe
do,
there is,
no,
the reason is from the data set.
So the way human understands is completely different from what machine understands. So you basically ask machine sometimes to do rote learning in the sense that it looks at the data, just memorize each and every example. So so you can think that human has expertise. Essentially, you can think of that human is trained on previous history for some domain knowledge that is not present in the machine. Just think about this case that human can, so a doctor have the different intuition, but doctor cannot process lot of data. Okay. Say, for example, the doctor cannot see a certain feature in the blood sugar level or something that the machine can detect. Okay. But the doctor has a different intuition that's very difficult to encode as a feature and feed it to the machine. So basically, the way machine looks at a problem is completely
different. So that's an
different.
assumption, actually. That's clearly an assumption, because that means that if I give the machine learning models background knowledge, and
how do you encode background knowledge to
there are a lot of work on this.
How do you give background knowledge?
There are a lot of work on this, different types of work on either it's structured knowledge or unstructured knowledge.
No.
First of all, what I'm trying to say is simple, actually. What I'm saying is that the fact that you are saying that machine understands a problem in different way than humans, it's an assumption.
So
There is no basis for the assumption as far as I understand.
Okay, so we can take it offline.
Yeah, definitely. I mean, I'm just trying to say that, of course, I agree for certain machine learning models, certain classifiers, that is true, but there are a lot of models which are now being equipped with knowledge and reasoning.
So I am not aware of any machine learning model in medical domain that replaces human. If it is not done that way, okay, if it is not, that replaces human. So that is going to take the final decision. And that is my point, that, it's very difficult to encode the entire doctor's expertise into the machine.
Yeah, that is definitely true.
That is exactly what
that's a specific, that's a specific domain,
specific
right?
Problems where it is difficult for a person or an entity to encode the human expertise into the machine. Of course, there can be, for example, ChatGPT is as good as human. I'm not talking about that application at all. There is no need for human. I'm talking for areas, for example, this medical domain application, where it's very, very difficult to, because I don't buy this, I really don't at all buy this argument that in medical domain, there are, it is very easy, or like there exists model where you can encode the doctor's knowledge completely in the model.
So what is doctor's knowledge?
That's not up to you. I don't know what is the doctor's knowledge, because it's very difficult to encode the doctor's expertise into the machine.
Yeah, so I think that also needs definition, right? So what is doctor's expertise itself? So what does the doctor's expertise come from? It comes from books and experience. That's how humans learn.
Correct.
Right?
Correct.
By reading and by experience through lifetime.
Not necessarily. There are practical work, so it's very complex.
Experience through lifetime.
So
that is experience.
No, experience comes from different ways. It comes from sequential learning, right? It comes from teaching. So now, of course, you can mimic the entire thing. See, I really don't buy this logic. You can mimic the entire world using machine learning.
Sure.
But certainly, that's what I'm saying. Since you cannot define the doctor expertise in a sound way, let alone you cannot actually implement doctor expertise and feed into machine model.
Yeah, sure. But even then, sure. Yeah, we can take it offline. Sorry.
Without going into a debate, you are thinking that machines can come part and humans can ideally solve the entire problem if they have time. This is your basic answer.
Not even that. Human can perform error in some, that's correct. Yeah. So human can do the entire thing if it is given time. That's correct.
Yeah, so my question was more broader, not related to specifically this section of the talk. So I think the underlying assumption is in data selection is that you already have lots of data. And I was wondering if this framework can be also used for active data acquisition, and essentially to preempt, scenarios where you don't have that data today, but then may lead to misclassifications in future, right? And this is very relevant in industrial settings where, on day zero, you probably don't have all the data, but then, you might have data in future, cases like that.
So in machine learning community, so I don't know what you mean active data acquisition. In machine learning community, what active data acquisition means, suppose you to go to the doctor and you tell that I have a fever, okay? And then the doctor suggests what test to perform, right? To find the disease. So maybe, one thing I can think of is looking in the feature space, and identifying areas in the feature space that are underrepresented, and thereby sort of targeting those specific areas in the feature space and trying to either acquire or generate data in those areas of feature space, right? So, absolutely. So you are talking more about uncertainties kind of sampling. So basically, if you have a less data in some regime, then the machine will be more uncertain about. Because at that point of time, since there is less data, you cannot commit on some points very certainly. So that's what I was saying. Like it's more like actively querying. Let's say during training time, you don't have an instance. You start with random sample. You ask the human to give me the queries. I query you, give me the level, like the true levels, as well as your confidence. So by that confidence, you can deduce some kind of estimate of the error. Now you train this model. You just apply this model, get an estimate out of S. Look at this machine model and search at what area machine is less confident about. Then for those points, you again query for the humans. So it's just because, this is, you can see this as more like an exploitation. And what you are saying is more exploitation. And that is something that can be useful. So this is an open kind of problem. We are still trying, like exactly what you have said, like, during active discovery of features, during training time itself, like I don't have access to this, this points, this C. I don't have any estimate of the error. So we start with some random points. I observe what the machine's performance is based on the random points. And then based on that, I see where human is uncertain and machine is uncertain, and then use those information to query more points. But we don't randomly query anymore. We use this information to get some stratified sample from the overall set to get an appropriate query from the human. So let's say where the machine is more uncertain, I will query those points, because since the machine is uncertain, I'm likely to outsource that to the human at the end. So I will ask, what is your error at the point? Because it can happen that machine is also uncertain at some points and the human is also worse, right? So to make that decision, to enable the machine to take that decision, you should query those points from human where not that the machine is bad at, but also machine is uncertain about.
I had one specific question on this topic as well. So how does this work at the time of inference?
Again, using a different classifier. So basically, let's say you find S, okay? And you find SC, complement of S, okay? So now this gives you two classes. One is S and V/S, okay? Now given X, train a classifier on this S D/S pair. So let's say S is 1 and SC is 0. So you train an additional classifier after you solve this optimization problem. And then suppose I give you an unseen example, I assign it to human based on whether it is, giving 1 or 0.
Understood, yeah.
But then there is a many chance of miscalibration. We have found that. Yeah. I know.
Okay. In the interest of time, let's wrap this up. And let's thank Abir and Rishabh. Small token for you. Small token for Ganesh.
Thank you. Thank you. Thanks for the invitation.